Hi everyone, welcome to Semi Therm Two-Phase Flow Cooling Online Summit. I'm Jennifer Arroyo, Editorial Director for Electronics Cooling. Thank you for joining us, and I hope that you've been enjoying the program so far. Our next session, Principles of Metal Foam-Based Cooling Systems, will be led by Metodi Zlatinov. Metodi is the technical lead of R&D at ERG Aerospace, where his specific focus is heat transfer applications. Previously, he developed cooling technologies for gas turbines at GE Aviation and later led the fluid design and hydraulic testing efforts for novel hydroelectric turbines at Natel Energy. In this presentation, Metodi will discuss the principles, advantages, and disadvantages behind designing effective metal foam cooling systems. Take note of the Q&A window in your presentation screen. You can submit questions you have anytime throughout the presentation for Metodi to address at the end. For technical issues, find the Help Guide button with the gear and wrench, which addresses common issues and ways to fix them. Feel free to start discussions with other attendees using the group chat window. So let's get started. Metodi, welcome.
Thank you, and welcome all to today's webinar on metal foam cooling solutions. Our goal will be to answer the what, where, why, and how of metal foam cooling. We will especially be focusing on the fundamental principles of how to design such systems, as well as what the future holds for two-phase applications. So what is metal foam? In simple terms, it is a rigid sponge made of metal. There are numerous types of such foams and numerous ways of producing them. Here, in the context of heat transfer, we're specifically considering open-celled metal foams, which consist of a network of interconnected ligaments that form cells with open pores. Some of the relevant features of such foams include a thermally conductive matrix, customizable structure and properties, small hydraulic diameter, high surface area, and high heat transfer coefficients. Last but not least, metal foams provide unique opportunities from a manufacturability perspective, as they can be machined, brazed, soldered, bonded, and processed with various coatings. Where metal foam comes into play in heat transfer applications is as a higher performing alternative to fins. Metal foam can be applied across the full spectrum of thermal management schemes, from natural convection to two-phase and phase change material cooling. As power electronics trend towards generating more waste heat in smaller packages, our goal is always to use the simplest solution for the application at hand, and the high performance of metal foam can significantly extend the range of applicability for a given cooling scheme, resulting in smaller, lighter, simpler, and safer systems. This is particularly the case in very high heat flux applications, where, for example, single-phase metal foam cold plates can handle heat fluxes typically associated with two-phase cooling systems, up to 200 watts per centimeter squared. And in the case of pool boiling and flow boiling, metal foam's high surface area and ability to disperse the phases and prevent departure from nucleate boiling or dry out result in higher heat transfer coefficients and critical heat fluxes. Metal foam also performs extremely well in solid liquid two-phase systems, typically referred to as phase change material or PCM heat exchangers. Here, peak thermal loads are absorbed into latent heat as the PCM melts, while a metal foam matrix provides crucial enhancement of thermal conductivity, allowing very uniform temperature profiles throughout the melting process. As mentioned previously, there are numerous metal foams and numerous ways to produce them. Duocell foam is rather unique among open-celled foams in that its ligaments are completely solid, with purity typical of that of the parent alloy, and its physical and thermal properties can be customized across a very wide range. Depending on the thermal and chemical compatibility requirements, the appropriate parent material can be selected from options including aluminum, copper, Inconel, and even ceramics. Then, the pore size and ligament cross-section are independently controlled to deliver the desired surface area, pressure drop, and metal volume fraction. Pore size is typically described by the number of pores per inch, or PPI. Meanwhile, as metal volume fraction increases, the ligament cross-section changes from triangular to circular, and that increases both conduction area and surface area in a way that is completely independent from pore size. Last but not least, unlike hollow ligament metal foams, dual cell can be compressed by up to 8 times without fracturing ligaments, making this a practical way to drastically increase surface area and effective thermal conductivity. But how do we go about designing cooling systems with this seemingly complex material? The design process is actually very similar to that of fins. Consider the fin and foam cores depicted above. In either case, you can express the heat flux in terms of a fin efficiency or in terms of an effective heat transfer coefficient on the heated surface. You can actually go through the exact same fin theory to derive an analytical expression for fin efficiency. The only difference is that in textbooks, one usually sees the final expression simplified in terms of fin length, fin thickness, and parent material thermal conductivity. Whereas for a more complex structure, like foam, we stop one step short of that and use empirically determined surface area per unit volume and bulk or effective thermal conductivity. Applying fin theory in this way, we can get a sense of the design space for foam heat exchangers by looking at the effective heat transfer coefficient as a function of foam thickness and relative density. The latter is just another term for metal volume fraction. Effective heat transfer coefficient is a measure of how much heat you can pull out per unit area for every degree of temperature difference between coolant and heated surface, and can be compared to a flat plate heat transfer coefficient to give you a sense of the enhancement due to foam. To generate the surface plot on the right, we have assumed a 30 pores per inch copper foam and a constant value for local film coefficient that is representative for water-cooled foam. Note the range of effective heat transfer coefficient on the vertical axis. A foam configuration with an effective heat transfer coefficient of 50 watts per square inch per degree C would pull out 1 kilowatt per square inch given a 20-degree temperature difference, and that is just with single-phase liquid cooling. Another thing to note is that in liquid and two-phase systems, the optimal thickness of the foam core is on the order of 0.1 inches, or about 3 millimeters, since beyond that point, the performance saturates due to fin efficiency effects. Another critical aspect of foam core sizing is related to thermal conductivity, and there are often misconceptions about the effect of compression in particular. For uncompressed foam, bulk thermal conductivity has been studied extensively, and the experimental results actually line up with a very simple theory, namely that 1/3 of the ligaments are aligned with the heat flux direction, hence the factor of 1/3 in the equation on the right. The other terms are metal volume fraction and parent material thermal conductivity. However, when you start compressing the foam, direction really matters. Thermal conductivity increases proportionally in the two directions perpendicular to compression, as you are effectively increasing the number of ligaments available for conduction per unit area. However, thermal conductivity actually decreases substantially along the direction of compression, since heat must now go through a more tortuous path. It is therefore very important not to compress in the wrong direction when designing heat transfer systems. While greater heat transfer augmentation is always welcome, the associated pressure drop is usually also of concern. Although foam typically results in higher pressure drop for a given mass flux, this can be mitigated by reconfiguring the inlet headers, or cores themselves, to direct flow across a wider dimension of the foam core, thereby reducing flow velocity. Since flow resistance scales much more strongly with velocity than does heat transfer coefficient, pressure drop can be managed in this way with minimal sacrifice in heat transfer performance. This design philosophy is not new. The diagrams here of oblique headers and folded cores are from the canonical heat transfer text by Case in London. The approach is also used in other areas of engineering, such as this labyrinth spillway on a dam. Yet more conventional thinned cold plates and heat exchangers do not usually resort to such architectures, and indeed, in many cases, they are precluded from doing so due to the unidirectional nature of fins. Therefore, when one is considering a drop-in replacement with foam, it is useful to think out of the box in terms of form factor and make best use of foam's advantages. Also note that it is quite straightforward to model the 2D and 3D effects in these designs using conjugate heat transfer CFD models with a porous media approach. Let us wrap up our discussion with examples illustrating how metal foam can be applied in two-phase heat transfer solutions. Here we have a case study on metal foam phase change material heat exchangers from the European Space Agency's ExoMars mission in 2016. As with most space applications, thermal management is limited by the area available for radiating heat into space. However, much higher peak loads can be accommodated using a phase change material, typically a paraffin wax, that absorbs the high heat load as it melts and then solidifies or recharges during periods of lower dissipation. This cycle is illustrated in the notional plot below. The trouble with most phase change materials is that they have a very low thermal conductivity. In this application, ERG Aerospace designed 3 phase change material heat exchangers using 40 pores per inch dual-cell aluminum foam compressed to about 30% relative density as a conductive metal matrix that was infused with the phase change material. This resulted in a 10-fold increase in effective thermal conductivity and less than 4 degrees in temperature gradient at all times during operation. Lastly, the application of metal foam in liquid vapor two-phase heat transfer is just emerging. The combination of high surface area and enhanced mixing holds great potential for improving two-phase systems ranging from passive thermosiphons to pumped two-phase to vapor compression systems. In any liquid vapor two-phase system, there exists a limit on maximum heat flux, the so-called critical heat flux, which is associated with too much vapor coalescing near the heated surface and obstructing heat transfer. In pool boiling and high mass flux flow boiling, such as in pumped two-phase systems, this phenomenon is referred to as departure from Euclid boiling and can quickly result in overheating of the component being cooled. Meanwhile, in vapor cycle systems that must evaporate virtually all liquid prior to compression, the term dryout is used to denote liquid film dryout in annular flows that occur toward the end of the evaporator. In both cases, the small hydraulic diameter and tortuous structure of foam can be very beneficial for dispersing the phases and extending the critical heat flux limit or delaying dryout. While there have been some recent investigations in this area, such as this work that shows flow visualization of phase dispersion at different flow rates, most efforts have thus far been limited to large pore-sized, uncompressed foams. Therefore, the most exciting research into small pore, compressed foams is still ahead of us. We hope this has been an informative introduction to the principles of metal foam cooling, and hopefully you're as excited as us to see how the nascent two-phase applications of metal foam will develop as more research focuses on higher performing, smaller pore size metal foams.
All right, we've had some questions come in, so let's get started. Our first one is, if brazing or soldering to metal base plates does capillary wicking of the molten metal plug the pores more than a few cells deep?
A good question. Actually, when using appropriate braze foil thicknesses and braze procedure, there's no risk of plugging any pores. And actually, the surface tension effects help collect the braze alloy around the base of the ligaments at the joint interface. So that actually helps ensure a solid braze joint, but there is no risk of plugging any pores just because of the scales of physical scale of the braze alloy thickness and the pore sizes.
All right, we have a question here. How do you characterize the hydraulic diameter and surface area of the foam?
That is also a good question. So obviously, whether you're doing fundamental testing to quantify heat transfer properties or build a correlation, or whether you're doing quality control, as we regularly have to do at ERG, you need a way to measure these geometric characteristics. Historically, pore sizes were measured optically, so you look under a microscope and you measure it that way. Whereas things like surface area was measured using physical absorption of gas molecules on the surface, a method called BET. However, recently we at ERG and also a lot of folks in academia have moved to using CT scans, which are much more reliable and give you a lot more information. So essentially, you take X-ray images of different slices of your sample, and then you post-process them into a 3D surface, which you can then interrogate with automated software to get surface area, pore size, and all that information.
All right, next we have one on what's the range of the pore sizes that are available?
So it depends on the material. So the foam can be produced with different types of materials, but the ones most relevant for heat transfer are aluminum and copper. The most common pore sizes are 40 pores per inch and 20 pores per inch. That said, don't forget that you can then compress significantly to decrease the effective pore size while increasing surface area, conduction area, and all that all those properties.
Okay, great. Is there any control on the shapes of the pores after compression?
The shape of the individual pores is, you do not really have control over that. However, you do end up with a orthotropic material that on average in each plane has mirrored out properties that are quite uniform.
All right, we have a question on what are the challenges to have composite metal foams with high thermal conductivity nanoparticles embedded for better heat transfer? Are these being investigated currently in industry research?
If the nanoparticles are referred to, the question refers to nanoparticles embedded in the alloy of the ligaments. That is not something that we're aware of as being researched. As far as incorporating particles interstitially within the pores, there are applications where that is being done not for heat transfer augmentation, but for things like catalytic reactions, where you have amines and other types of particles that are put interstitially within the pores, and then metal foam provides thermal conductivity, where all those particles do their job on the chemical reaction side.
All right, there's a question here on does dust accumulate inside the foam after prolonged usage, reducing airflow? And how do we clean that for bigger size foam structures? That
is a good question, and unfortunately there isn't too much data on that. From our products, we haven't experienced significant degradation over time in performance. And as far as cleaning, if the component can be removed, it can be cleaned with air, either by forcing air in the opposite direction or some other standard method for cleaning heat exchangers and heat transfer media like that.
Okay, next we have, what is the range of thermal conductivity for an aluminum metal foam?
Yeah, so in one of the slides we showed the expression for thermal conductivity for uncompressed foam. And so if you can just kind of plug in some numbers, you end up with you can kind of estimate what those numbers are, but once you start compressing, you can usually go up to about 40 watts per meter Kelvin. But again, it will depend on the application and how much pressure drop is allowable.
Okay, we have a question here about how does foam heat exchangers compare to solid copper heat exchangers in electronics?
I'm sorry, could you repeat the question?
How do foam heat exchangers compare to solid copper heat exchangers in electronics?
Okay. Yeah, so we typically have, comparing to state-of-the-art cold plates or similar type of cooling solutions, we typically end up with a thermal resistance that's about half of state-of-the-art technology.
All right. Our next question is whether or not metal foams can be used in heat transfer.
Absolutely. They're an excellent extended surface for heat transfer, for augmenting heat transfer.
Next up, we have, what is your insight on replacing fins with thin metal foam in natural convection applications?
Natural convection applications are also a situation where metal foam works quite well. You can really reduce the overall volume of the heat sink. And because the pores are so open, you can really get quite a lot of airflow through there, even with natural convection, even if you don't have a fan or forced convection.
Okay, here's a question on what the optimal density for two-phase heat transfer is.
So that would depend on the cooling requirements in the specific application. But also, it's an area that is actively being researched, metal foams for two-phase cooling. So it's hard to give a specific recommendation. One thing, I suppose if I was pushed, I would have to say a good place to start is smaller pore, so 40 ppi, and probably something like a 10% foam compressed by a factor of 2 to 20% density.
Okay, we have a question here on is wearing of the PCM capsule possible?
The PCM capsule, I assume that means the the housing that encases the metal foam infused with the phase change material. There usually isn't any risk of wear on that external structure. And we have not experienced any problems with cycling or thermal fatigue over time.
Okay, getting back to pore size, we have a question here. What are the current limitations of the geometry for pore size and porosity?
Yeah, so again, it kind of depends on the material, but for metals like copper and aluminum, which are primary interest in heat transfer applications. The comfortable range is down to about 40 ppi. We can go to smaller pores, but it starts becoming less repeatable.
All right, next up we have, what are the radiation properties of metal foam?
That I'll have to follow up on. There is research out there. Locally, the radiation properties are the same as the base material in terms of emissivity and that kind of property. As far as the effective radiation properties due to reflection internally within the structure from ligament to ligament, the overall effect and whether there's any kind of attenuation associated with that, I would have to do a little bit more research before I can answer.
Okay, we have a question about the mechanical characteristics of the foam. Is it strong enough to hold moderately high internal pressure?
The short answer is yes. So metal foam has many applications beyond heat transfer, including numerous structural applications. It is used in sandwich panels, as energy absorbers for impact. So metal foam has been characterized both in compression and tension fairly well, and it has been proven in pressurized environments as well. And furthermore, the brace joint is typically not the weak point.
Okay, our next question is how to join the metal foam with a solid metal?
There are different ways you can do it. If minimizing contact resistance and is a primary concern, as in many heat transfer applications, brazing is preferred. Another way to do it is with soldering. Aluminum foam can also be nickel plated, which makes it even more easily solderable. And then there are also various ways that you can bond foam to solid surfaces that come with their, bonding comes with an associated penalty in terms of thermal resistance, but that is a lower cost alternative as well.
All right, well, we're going to go ahead and wrap up the questions there. Thank you again to Metodi for speaking with us today. If we weren't able to get to your question live, don't worry. All of the questions submitted will be posted on our website along with answers. Watch out for an email from us within the next 24 hours. We'll be sending you a link to the on-demand version of this presentation. I hope you can make it to our next session. Starting at 12:15, you'll hear about experiments conducted to characterize the cooling limits of novel cold plates. Once again, I'm Jennifer Arroyo with Electronics Cooling. Thank you for joining us for Semi Therm two-phase flow cooling online summit.